Welcome back. All right, so we are talking about how to use the Laplace transform to make PDEs simpler, to solve PDEs, specifically by Laplace transforming out one of the independent variables so that this partial differential equation becomes an ordinary differential equation. One of these, I have done this on the heat equation. This lecture, I'm going to do it on the wave equation. And just to remind you, you can definitely solve these kinds of heat equations and wave equations on infinite domains where with nice boundary conditions where things decay to zero using the Fourier transform. But if you have a one-sided semi-infinite domain, we need to do it with the Laplace transform. And we'll need boundary conditions and initial conditions. So for the wave equation, UTT, the second partial derivative of u with respect to time equals c squared uxx, the second partial of u with respect to space. Here, let me just write down that u of x and t is basically going to be the height of some rope. So every kid, when you were younger, right, you like flipped a rope and that sent traveling waves down that rope. So we're basically going to be shaking a rope at the left end and sending traveling waves down that rope. So this is position x equals 0. It goes to x, tends to infinity. The rope is being shaken at one end, which generates traveling waves, generates traveling waves. And u of x and t is going to be kind of the height or the displacement of this rope at a location x at a time t. So this is essentially kind of the height of rope at x comma t at space at point x at time t. Good, and so now I need some initial conditions and some boundary conditions. And so the first thing I'm going to do is I'm going to say that I'm going to be shaking the rope up and down, and I'm going to say that I'm going to try to keep my boundary conditions blue. So I want to say that this up and down motion is f of t, some forcing in time. So I'm going to say that u at location x equals 0 for all of time is equal to, sorry, it's so squeaky, f of t, this is my boundary condition. Oh, that's real squeaky. And then my initial condition is going to be that at time 0, I'm going to have u of x at time 0 equals 0, and I'm also going to have that the derivative, that it's not just at position 0 passing through with some velocity, but that it really has 0 velocity, that u sub t at x at time 0 also equals 0. So the position is 0 everywhere at time 0, and the velocity is 0 at all locations x at time 0. These are going to be my initial conditions. And we're going to Laplace transform this PDE, and we're going to use the initial conditions and boundary conditions to get a solution. Okay, and again, you always have to think to yourself, do I Laplace transform in space or in time? Because the whole point here is that we are removing one of these independent variables. We're turning it into a Laplace variable, which is essentially going to be like a constant compared to the other variable. And so you have to decide, am I Laplace transforming in time or in space? And remember, when you Laplace transform something that has a second derivative, you're basically going to get s squared times that function plus s times the first derivative of the function plus the second derivative of the function evaluated either at 0, at 0. And so whichever, if I have two boundary conditions or if I have two initial conditions, I'm going to use the one that I have two of and Laplace transform in that variable. Since I have two initial conditions in time and two time derivatives, if I Laplace transform in time, I'll have enough information to satisfy that Laplace transform. So you should actually try this. Try to Laplace transform in space, and you'll run up against a wall pretty quickly because you won't have enough boundary conditions. So that's like a good exercise I ask my students to do. So we're going to, maybe I'll do this right here. So we're going to Laplace transform in time. So my markers are all squeaky because I've been here all day filming. So I hiked up from my home to the university with a guitar on my back to do the wave equation lecture. Now I'm doing Laplace transforms. It is the evening, it is a holiday, and my pens and I are both feeling very squeaky and dry. But you know, I know that many of you are learning this material in nights and weekends. You have a full-time job, maybe you have a family, and you're learning this in your spare time, and that's why I am teaching you in my spare time, because it matters, because you're putting in the time. So we're going to Laplace transform in time, and we're going to use our two initial conditions, hopefully, to satisfy that initial data in this Laplace transform. And that's because I have two time derivatives and two initial conditions. So Laplace transform in time is actually quite simple. It's s squared u bar of x comma s. So remember, u is a function of space and time, but I'm Laplacing in time. So now u bar is a function of x and my Laplace variable s. My second derivative in time became an s squared times u bar. And then remember, when you Laplace transform something that has a second derivative, you also have a minus s times the first time derivative of x at time 0. This is kind of my first initial condition at time 0, minus u of x comma 0 equals c squared u bar xx. And remember, if I Laplace transform uxx with respect to time, that's the same as taking the second partial derivative of u bar, my Laplace of u with respect to time. You should just work that out on a little napkin or piece of paper. It's really simple. If you have a function of space and time, I can Laplace transform it in time and then take two partial derivatives, or I can take two partial derivatives in x and then Laplace transform in time, and they're equal to each other. So this is just u bar sub xx. Now, the nice thing is that my initial conditions for this and for this are both 0. I did that on purpose, obviously. But it's a physical scenario. My rope started out, I laid it flat on the ground at 0, and I'm going to start whipping it. That's a very physical initial condition, is that these are both 0. So these are 0 by my initial conditions. So that's super cool. Right out of the gate, we Laplace transform this thing. Our initial conditions allowed us to kill these two kind of pesky terms that always crop up when you Laplace transform something with multiple derivatives, these kind of initial condition terms. And now I just have my equation s squared u bar equals c squared u bar xx. And this is an ordinary differential equation in x. This is a second order linear ordinary differential equation in x. We know how to solve ordinary differential equations because we got rid of, here we had two partials, partial in x and partial in y, in t. Here, this only has partials in x, so it's an ordinary differential equation. So this is, I'll just write that. This is an ODE in x. And so we know how to solve this ODE in x using kind of simpler math. PDEs are generally thought of as more complicated than ODEs. It's more involved to solve them. So this should be easier to solve than this. So let's solve this expression here. I think what I would probably do is divide both sides by c squared. So I have u prime prime. I'm just going to write it out. So I'm going to have like u bar xx minus s squared over c squared u bar equals 0. And so this thing is going to have eigenvalues plus or minus root s over c. And so those are going to be the two basic solutions are going to be, I'm just going to write it out here. So the two basic solutions are going to be the two basic solutions are going to be u bar of x comma s equals an e to the plus, or an e to the minus s over c x, and an e to the plus s over c x. And these each have coefficients out front. There's going to be, some a and some b coefficients. And just like when we did this for the heat equation, I hope you've seen that one, these coefficients are constants with respect to x, but that means that they can be functions of s. They can be whole transfer functions, a bar of s and b bar of s. And we're actually going to determine these constants, these transfer functions, using the boundary condition here that we haven't used yet. So we already used our initial conditions. We're going to determine these using our boundary conditions. Good. Let's see. All right, and we know that when we flick this rope, it's never going to blow up to infinity. Like, no one's that powerful. Maybe Thor, if he flicks a rope, he can make it blow up at infinity, but we can't. And so this thing has to decay to 0 as x goes to infinity. So that right out of the gate kills this positive term here. So this term, basically b has to equal 0 for a bounded solution. And I'm kicking myself because this should have been a blue x and a blue writing, because this is kind of a boundary condition that it has to remain bounded. This should be blue b equals 0, okay, unless you're Thor. And so now this is the only term in the solution. Super simple, right? Like, we Laplace transformed, we used our initial conditions. This is the only term that can be in the solution. And to some extent, this is really easy, because now we're going to use this left boundary condition where we set x equal to 0. E to the 0 is 1. And so a bar s is equal, a bar s is equal to u bar of x equals 0, comma s. And u bar of 0, comma s is just the Laplace transform of my forcing f of t. This u bar is just the Laplace transform of u at spatial location x equals 0 at time t, and that's f of t. So essentially, u bar at x equals 0, comma s is just the Laplace transform of my boundary condition. So this entire a bar s is just my Laplace transform of my boundary condition. Very, very simple. This is actually like an easier example of Laplace transforms for PDEs than the heat equation. Maybe I should have started with this one, but I'm ending with this one. And so the solution, I'll just write it here. So the solution, the full solution in Laplace domain is u bar x comma s equals, I'll call this f bar. F bar of s is just the Laplace transform of my forcing f of t, times e to the minus s over c x. That's it. That's my solution. This is my entire solution to this rope being shaken one-way kind of semi-infinite domain wave equation. Now, I'll have to inverse Laplace transform this to get something that has a time variable instead of a Laplace variable. That's a little bit tricky. So this is in frequency. In time, I'm going to get u bar of x comma t equals, and you're going to have to take my word for it, that when you inverse Laplace transform this construction here, some function of s times e to the minus s over c x, essentially what this does is it kind of time shifts this function. So what this is f of t minus x over c. You could either compute this using the inverse Laplace transform formula. You could look in the back of a textbook for the lookup table. You could do this in Wolfram Alpha or Mathematica. You could derive this from scratch. But this is the answer: is that this expression here essentially shifts the solution f of t by x over c. That's how much it shifts it by. And there's a detail here. This function is only defined, I should have probably written this down here, this is only defined for t greater than or equal to 0 and x greater than or equal to 0. And so I have to multiply this by a Heaviside function, and my Heaviside function is t minus x over c. This is kind of a technical mathematical detail. The Heaviside function, literally, I'll draw you a picture of it, but it's something that only turns on when this is positive, okay? Because that's really important. This argument has to be positive for this solution. So this is actually the honest-to-goodness solution. This is the solution in time. This is the solution in frequency domain. Okay, so now what I'm going to do is I'm going to show you what this Heaviside means, and I'm going to draw you a picture of, oh, this is not a U-bar. Sorry, you should be screaming into your screens right now. This is U, not Laplace transform. This is in the original coordinates x and t, is this thing. So I'm going to show you what this Heaviside function is, and then I'm going to draw you a big picture of kind of how information propagates in a space-time diagram for this problem. Okay, so the Heaviside function is pretty simple to visualize. Essentially, I'm going to look at this Heaviside function, and I'm going to first fix x and vary t, and then I'm going to fix t and vary x, and we're going to see what happens. The Heaviside function is a function that is 0 when the argument is less than 0. When the thing inside is less than 0, it's 0. And it becomes 1 when the argument inside becomes positive. So it's like this. And it kind of jumps discontinuously at that location. So we're going to fix x and vary t. So this is in the t direction. And so this argument for a fixed x, this argument becomes positive, and this Heaviside jumps to being positive when t equals x over c. So at some location, basically there will be some time x over c after which information will hit that location x. So there is a time before which information doesn't reach a certain location in x. That's kind of what this Heaviside is saying, is that it takes time for information to propagate. I'll draw you another picture in a minute. The other way to understand this Heaviside function is to fix t and vary x. It's a little bit more complicated, not really. If I fix t and vary x, this thing becomes positive when x equals c times t. So similarly, when x equals c times t, this thing will jump up and information will start propagating at that location x. So at a fixed time, there will only be certain x's where information will have propagated. Ooh, I really botched this. This is the inverse of this because this is a minus sign here. It's x less than ct where this is positive. For x less than ct, this is positive. And for x greater than ct, this is actually, the argument is less than 0. And so my Heaviside is actually like this when I fix time and vary x. Convince yourself of that. Remember our Heaviside function, when this argument is less than 0, the Heaviside is 0. And when this argument is greater than 0, Heaviside is 1. And so if I fix t, then for x less than ct, this thing is positive and I have 1. And when it's greater than ct, this argument is negative and I have my Heaviside 0. It's a little messy. But at the end of the day, what we're trying to do is solve this PDE, the wave equation. This is the solution. That's what you get when you Laplace transform. You use your initial conditions. You use your boundary conditions. You get that it's only this term in Laplace domain, this term right here, where f bar is the Laplace transform of my forcing, my boundary condition. And when you inverse Laplace transform, you get this weird relationship that you get this shifted version of my forcing times a Heaviside, and my Heaviside behaves this way. So now I'm going to draw you a picture physically of what's happening, and this is going to make, I think, way, way, way more sense. Okay? So our forcing, and I'll draw it in blue, our forcing f of t, literally in time, is going to be some forcing. Remember, you're a kid and you're just whipping this jump rope, it's draped out in front of you and you're just whipping this thing at some, F, and you're trying to make it as crazy as possible. That's the F that you're sending propagating through this rope, okay? So that's F of t. And so now what we're going to do is we're going to draw something called an xt diagram. And this is used all the time in physics, especially in things like shockwave physics or the propagation soliton physics and optics and lasers. If you look at shock waves in fluids like over a missile or a bullet, you're going to be drawing xt diagrams. xt. And so now this forcing in time, it's at location x equals 0. So it's at x equals 0. In time, this is my forcing function. So I'm forcing this thing at x equals 0 at time t. This is my boundary condition forcing. And essentially what happens is along this characteristic line, x equals ct, if x equals c times t, this thing is equal to 0 and this is equal to 0. Essentially what you find is that information propagates in this xt diagram at a certain speed. So all of this information propagates linearly like this. So what happens is if I go to a downstream location x, let's say I go to this location, x whatever, then at a certain time in the future, my initial forcing that I've already done is appearing at that downstream location x. So that forcing position will essentially be traveling down that rope. This is it traveling down that rope to farther and farther locations downstream, to farther and farther x's as time progresses, as that information has time to travel down to those downstream locations. So this is the line. This line here is super important. This basic line here should be in a different color probably. This line here that's kind of pink and yellow, this is the line x equals ct along which information propagates. So this is kind of a characteristic. We call this the wave front, or the characteristic line of this problem. And below this here, u equals 0, because no information, so at a really far downstream location, x, 10, 20 meters downstream, for short times, no information is propagated there, so it's still equal to 0 until enough time has passed that this initial wave front can reach that location. So this is the wave front. This is literally that first part of the motion when I just started turning this thing on at time 0 that is now traveling at this speed, and that forcing pattern is traveling downstream on my rope. So really important in capturing physics, traveling wave physics for the wave equation. Pretty much the wave equation has what's known as traveling wave physics. That's where the word wave comes from, are these, these waves that are kind of coherent and traveling in time with these xt diagrams. Okay, so that's the kind of intuition you can build when you solve these things using the Laplace transform, and you can do it on weird domains. So we are used to thinking of infinite domains where x goes negative infinity and positive infinity, in which case if I forced my rope in the middle of an infinite rope, those waves would travel both left and right. I would get waves going in both directions, the two-way wave equation, until either it dies out at infinity, or until it hits some kind of boundary condition that's so far away that maybe it starts reflecting back. Like maybe it's in the middle of a gigantic guitar string or something like that. So those are the kinds of things you can play around with, changing the boundary conditions, changing the size of the domain, and thinking about how these solutions change. But this idea of an xt diagram, this is why we need the Heaviside function, literally so that there are certain times at which information will hit that x location, and there are certain x locations where the information is 0 until a certain time is reached. Okay, this is an example of how you solve PDEs with Laplace transforms to turn them into ODEs, and then to use initial conditions and boundary conditions. All right, thank you.